So the exponential model A is equal to 695e to the 0.009t describes the population A of a country in millions T years after 2003. Use the model to determine when the population of the country will be 734 million. Now, this right here, the 695, that's in millions, the base population, and the A in front is the new population, basically, right? So, we plug everything in. So A is equal to 734 million, so that's A, so A is equal to that. We are solving for T, so T is the unknown. Let's plug it in. 734 equals 695e to the 0.009t power. At this point, I would try to get the e by itself. So I need to undo the multiplication of e by 695 by dividing by 695, and whatever I do to one side, I do to the other. Those would cancel out, leaving me 734 over 695 is equal to e to the 0.009t power. Then I would take a natural log of both sides. That would give me the natural log of 734 divided by 695 is equal to 0.009t to the natural log of e. I pulled this exponent to the front. Now the natural log of e is 1. So we are just left with the natural log of 734 over 695 is equal to 0.009t. We undo the multiplication of t by 0.009 by dividing by 0.009. Whatever we do to one side, we do to the other. The 0.009 cancels out on one side, leaving me t is equal to the natural log of 734 over 695 all over 0.009. Prehistoric cave painting were discovered in a cave in France. The paint contains 15% of the original carbon. 14. Estimate the age of the painting. We have an equation A is equal to A initial times E to the KT, where A in this case is 15% of the original, equal to the original, E, K, T. 15% is equal to 0.15, A initial equals A initial, E to the KT power. Next we can divide both sides by A initial. So let's cancel out, leaving me 0.15 E equals E to the KT power. Next I would take the natural log of both sides. Gives me the natural log of 0.15 equals the natural log of e to the kt power, but I'm going to pull that kt to the front, so it's going to be a kt. Next, natural log of e turns into a 1, so we end up with the natural log of 0.15 is equal to kt. There's two pieces of information that could have been given here. One is they could say the half-life was 5,715, in which that would allow you to solve for k, and then when you solve for k, you get negative 0.000121. So I'm gonna assume that he's not going to make you solve for this. I did an example of that in the homework where you can, given a half-life of t, you can solve for k. I'm going to assume that k is going to be given. So at this point, I'm just going to plug in my k. So it's going to be the natural log of 0.15 is equal to k, which is negative 0.000121 t. And since I'm trying to solve for t, I'm going to undo the multiplication of t by negative 0.00012 by dividing by negative 0.000121. And whatever I do to one side, I do to the other. And that means t is equal to negative natural log of 0.15 over negative 0.000121. The half-life of the radioactive element plutonium-239 is 25,000 years. If 16 grams of plutonium-239 are initially present, how many grams are present after 2,500 years? 50,000 years. 100,000 years. Every 25,000 years, the amount is going to be halved. So after 25,000 years, you're going to have half. And after 50,000 years, you're going to have half of a half, which is 1/4. And after 10,000 years, you're going to have 4 times, right? So it's not going to be 1/8. It's going to actually be 1/16. So let's actually see how the math works out. If you wanted to come up with your own equation, you would say A is equal to A initial times e to the kt power. Dealing with a half-life, we would have half of A initial equal to A initial, the initial amount, times e to the k t, and t in this case we actually know to be 25,000. And what this means is after 25,000 years, t, we should have half of the initial amount. So the next step is I'm going to divide both sides by A initial. Those cancel out. And that leaves me 1/2 is equal to EK times 25,000. Now I take a natural log of both sides. So natural log of 1/2 is equal to the natural log of e to the k times 25,000. Then I'm going to pull this exponent from the top down to the front right there. And that gives me natural log of 1/2 is equal to 25,000 k natural log of e. Now natural log of e is equal to 1, so it just goes away. And we end up with natural log 1/2 equals 25,000 k. We undo the multiplication of k by 25,000 by dividing by 25,000. And whatever we do to one side, we do to the other. That gives me k is equal to natural log of 1/2 divided by 25,000. That gives me approximately negative 0.0000277. Go back to the original equation. A is equal to A initial times e to the k, which is negative 0.0000277 t. And then we plug in the numbers they give you. So after 50,000 years, we already know it's going to give you 1/4 of whatever the original was anyways, but this is just going to verify that. You could just simply plug in the 25,000 in there, the 50,000, or even the 100,000 in there, and it would just verify the amount that you're going to get. Section 8.1. Write the first 3 terms of the sequence. The first term of the sequence is going to be 2n, n being 1, the first number of the sequence, over n. N again is 1 plus 4, which gives me 2 times 1, which is 2, and 1 plus 4, which is 5. The next term in the sequence is independent, so everywhere it has an n. Instead, now we're going to plug in a 2. So we say 2 times 2 over 2 plus 4. 2 times 2 is 4. 2 plus 4 is 6, and we can reduce this fraction by dividing both the numerator and the denominator by 2 and get 2/3. We have the third one in the sequence is going to be 2 times 3 over 3 plus 4, which gives me 6, 2 times 3, over 3 plus 4, which is 7, 6/7. The next one is a recursive sequence, so we have to plug in the previous one into the next one. The first one, the sequence is already given. It's 7. So we were looking for the second one in the sequence. So everywhere I have an n, we're going to plug in a2. So a subscript 2 minus 1 plus 5. Well, 2 minus 1 is 1 plus 5. And we know the first one in the sequence is 7. So we do a substitution. 7 plus 5, which gives me a 12. Next, we're looking for the third one in the sequence. So wherever there's an n, we plug in a 3. So it's a subscript 3 minus 1 plus 5. 3 minus 1 is 2 plus 5. And we know the second one of the sequence is a12 because we just solved for it. 12 plus 5 is 17. The next one we're looking for the first one in the sequence. Wherever we see an n, we plug in a 1. 1 squared is 1. Over 1 factorial is 1. 1 divided by 1 is 1. Now we're looking for the second one in the sequence. So wherever we see an n, we plug in a 2, which gives me a 2 squared over 2 factorial, which would be 2 times 2 is 4, over 2 factorial, which is 2 times 1, which is just 2. 4 divided by 2 is 2. Then we have the third one, which is everywhere we have an n, we plug in a 3 now. So we have 3 squared over 3 factorial. 3 squared is equal to 9. And 3 factorial is 3 times 2 times 1, which is just 6. So we have 9 over 6, 9 divided by 3 over 6 divided by 3. 9 divided by 3 is 3, and 6 divided by 3 is 2. We want to evaluate the expression 18 factorial over 3 factorial times 16 factorial. 18 factorial, we are going to write it not as a factorial, but without a factorial until we get to 16 factorial. So 18 factorial is equal to 18 times 17 times 16 factorial. And we're stopping at 16 factorial because we have a 16 factorial in the denominator. And that will allow those 16 factorials to cancel each other out. And that leaves me 18 times 17 over 6 factorial, which is 3 times 2 times 1, which is basically a 6, right? So 18 times 17 over 6. 18 divided by 6 is a 3. 16 goes away, turns into a 1, which leaves me 3 times 17, which is 51. Next, we want to find the indicated sum from 1 to 4 for 2i multiplied by I plus 3. So first we need to find those different i's, right? So for when I is 1, it's 2 times 1 times 1 plus 3 within the parentheses. 2 times 1 is 2, and 1 plus 3 is 4. 2 times 4 is 8. So when I is 1, this is what you get. We also want to add that to 2 times 2 multiplied by 2 plus 3. 2 times 2 is 4. 2 plus 3 is 5. 4 times 5 is 20. The next one in the sequence, now we're dealing with 3. So again, we start with I is equal to 1, and then we're going to finish with I is equal to 4 over here. So we've already done the first two. Now we're on to when I is equal to 3. So we're going to say 2 times 3 times 3 plus 3. 2 times 3 is 6. 3 plus 3 is 6. 6 times 6 is 36. Next, we're going to do the fourth one in the sequence. So everywhere I see an I over there, instead I'm going to be plugging in a 4, which gives me 2 times 4, parenthesis, 4 plus 3. 2 times 4 is 8, and 4 plus 3 is 7. 8 times 7 is 56. This is equal to 120.